session of the last talk of this session. So please stay here. Yeah, it's by Marco.
Yeah, good luck.
Yeah.
Scigliuzzo.
Okay.
It's fine.
Sorry. Here is the clicker, and if you want
It's
the green
fine.
laser
I'll just
pointer,
take the
like
clicker.
this.
Can you guys hear me? I guess so. Okay. Good evening, everyone. My name is Marco Scigliuzzo. I'm a postdoc in Professor Kippenberg's lab at EPFL in Switzerland. And today I would like to show you the last results on collective dynamics in circuit optomechanical systems. So before diving in the experiment, I just would like to remind you the platform that we use is basically a microwave cavity whose capacitance is modulated by a mechanical oscillator. And we can map this circuit directly in quantum optics language with the standard parametric optomechanical coupling. And in principle, we can even linearize and having a beam splitter interaction where the effective coupling is enhanced by the photon, intracavity photon occupation. And this platform has been widely used to obtain a very large number of experiments, and here I just put a few of them. And importantly, in the past, let's say 10 years, also multimode optomechanics are gaining more and more attention. And we think that this platform, when we have a single microwave mode controlling many mechanical resonator, is useful for quantum technology. For example, if you want to do quantum simulation. But all these platforms, especially in superconductive circuits, still have some difficulties. And for example, if you want to make many resonator of the same frequency, that is challenging from the fabrication point of view. And we want to overcome this challenging using this new technology that we developed at PFL, where the top electrode doesn't have any buckling, is very straight. You can see here a FIB cut. And these are mainly three advantages. First is that the frequency is much more controllable and reproducible. Second, tensile stress that this aluminum film experience at cryogenic temperature boosts the quality factor when we cool them down. And the third benefit is that we can implement some dissipation dilution on the clamping point. And in fact, as you may have seen from the talk this morning from my colleagues, we demonstrate that the quality factor of these cavities is indeed very good, up to 40 million. And it's also possible to use this multimode optomechanical system for doing quantum simulation, for example, in this strain graphene lattice model. So what do I want to use this platform in this experiment? We want to have many mechanical resonator, all resonant, all of the same frequency, just controlled by single microwave cavity. And you can think about that even if from the design point of view you try to get exactly the same frequency, due to fabrication imperfection, you will always have some scattering in the mechanical frequency. So here I just use this cartoon to show that indeed even a nominally identical sample or nominally identical mechanical resonator will have some scattering frequency. And indeed we can write the evolution equation for this system and taking into account different noise, different fluctuation of frequency. And in particular, we can consider that increasing the pumping on the red side band, we can control the effective optomechanical coupling. And indeed, we can solve this equation as a function of the pump power, or in the same language as a function of the intracavity photon number. And what we see is indeed that at very low intracavity photon number, the frequency, the mechanical resonator behaves a single individual element. but at some point, for some value of photon number, indeed we see a transition to a collective dynamics. And this is true both for the frequency of this mechanical resonator, but also for their bandwidth. But crucially, this is one of the main points of the talk, is that this transition point, when you get to the transition, strongly depend on the disorder. Here, for this simulation, for the solving, for the numerical solution of the equation that I showed before, I used the exact same disorders that we get from the fabrication runs, and you can see that the mechanical disorder, the mechanical variation of different frequency of the mechanical resonator, is of the order of 0.1%. And here, indeed, I want to show that this critical photon number threshold, where you see the kickoff of the collective mode, strongly depend on the disorder of the mechanical resonators. So how do we want to implement this? Instead of having a single microwave mode that connects to all mechanical resonator, we choose to have a collective microwave modes in order to keep the single element as one mechanics coupled to one microwave resonator. And when we fabricate it, this is how our sample looks like. You can see that there are 6 identical microwave resonator coupled each of them is optomechanically coupled to a nominal identical mechanical resonators. And indeed, for exploring this system, we can choose among 6 different microwave modes, because there are 6 microwave cavity that will hybridize. And in particular, if we now just take a single tone spectroscopy, we can identify all the modes, and we can concentrate for the rest of the experiment just on the lower frequency modes. And the first thing that we want to study is the frequency dispersion, like our scattering in frequency, and the line width of our mechanical mode. And as the previous speaker showed, we do this with the optomechanical induced transparency. We have a low power probe that scans among the cavity frequency, and we increase our red attune pump in order to increase the photon number, or equivalent to the effective coupling or line width of our mode. And you can see these are each trace, and on the y-axis we're just increasing the pump, or equivalently again the intracavity photon number. And if we zoom in this region, we can see 5 modes, 1, 2, 3, and these are 2 very, very close modes. And I just want to highlight that this is just 1 kHz, and in this 1 kHz regime, we managed to put 6 or 5 megahertz frequency resonators. And even more importantly, we can see that there is a transition around 10 to the 7 intracavity photon number between isolated mechanical resonator to a collective dynamics. And if we extract the line width of each individual mechanical resonator, you can see that at the beginning we have indeed 5 or 6. Here I'm also considering unfortunately one of the mechanics is very far off. So here I'm plotting all of them. We can count all 6 mechanical resonators that behaves exactly as individual resonators. But when we reach this critical photon number, this threshold, we see that there is one mode, that is the collective mode that keep increasing its line width, and all the other dark modes keep trying to restore their original line width. And in particular, this mode is again the 6th mode that end up very far from the other mechanical modes. And we can, as well, we can just investigate the spectrum. And we're also interested in the spectrum because through the sideband we can estimate the population. And one of the idea of this measurement, where again you can see all 5 resonators very close, and on the left panel is just the zoom of the frequency. And we can use this frequency spectrum in order to obtain the mechanical occupation of the collective modes. And the idea is to show that the collective mode is indeed cold, very close to ground state, while the individual mechanical resonator are still very warm. And with this, this is my last slide. So I show you that indeed we observe collective dynamics, and as a very straightforward experiment, we want to show that we can cool down this collective mode to the ground state while keeping each individual mechanical resonator still warm. And one way to show this, it will be also introduce auxiliary microwave cavity for readout each single mechanical resonator. And future experiment will include the squeezing of this multi-mechanical mode, because you can consider that now we have a collective mode, so we have boosted mass, boosted dimension, and possible also have some way to study localization and entanglement in these mechanical modes. And with this, I just want to acknowledge all the people from circuit team and Tobias group. Thank you.
Okay, let's thank our speaker. I hope you